All right, let's get started. So as I said in an announcement, there's a talk tonight by a former ASU industrial engineering student who actually took this class, I think, back in 2017, who now works at Disney. His operations research there is coming back partly on a recruiting visit and partly to talk about how they use operations research at Disney. And his particular talk is how they use discrete event system simulation to optimize certain aspects of the park. In this case, certain aspects of a restaurant at one of the parks. So I thought this was really relevant, and I think it may actually seed some ideas for your final project to see a real project like this being used out in industry where they're using simulation tools. So totally optional, but I created this bonus assignment that if you go to the talk, I've got these 5 questions that I'm hoping you can answer very briefly, so points for concision. And so the response should be 1 page maximum, less than a page definitely okay. And so if you have the time and are interested, attend Noah's talk and answer sort of, he's going to talk about the input models that they use. Well, I'm looking for what are some of the technical choices. So which input models? How did they choose these input models? There's going to be a number of different ways, but I want you to sort of capture some of the technical qualities that he'll report there. And feel free to ask questions as well. So what are the constraints that were placed on the model by the leadership? You mentioned that that's going to come up in the talk. How did the results of the simulation actually change the operations at this particular park? And then he's got, why was simulation used as opposed to, say, linear programming? And what platform or platforms did they use? So if it was an Arena, then was it FlexSim? Was it Simio? Did they have their own custom program? How did that work out? So those are sort of the things that I'm looking for if you go to the talk to look out for, and then write up, again, something less than a page that answers these things. And then I'll grade those and give you up to 5 points that go into the homework category. So each homework is worth 30 points, and the entire category is worth, I forget, 10 or 15% of your score. And so that will just get added on top of your homeworks. And if you don't do it, that's fine too. It's optional. It's out of 0. Any questions about that? Again, it's today at 6 p.m. in Brickyard 210. So today, now we're finally getting into random number generation, which was I've got this up here as well as another reminder, same info. So random number generation. So getting into that, we've got homework D2 has been posted for a while. It is technically it's due the date of lecture E2, but I've got this special late policy that I've now put on both C2 and D2. So that basically means that C2 is going to be due, actually, I don't want to say due, but because there's no late policy, but the last time you can turn it in without penalty is Sunday, and then E2 there'll be the Sunday after it's formally due. So if Canvas allows you to upload, then you won't get penalized. If it doesn't allow you to upload, you're too late. So it tells you when it's available, and then also if you read the assignments tell you when they're available too. So I still list the original due date because I want to be true to the syllabus, but I'm just sort of temporarily postponing the late policy just for these 2 so that you're sure to be able to see the content in class before you turn them in. Okay, so there's those. Oh, and by the way, I have submitted a ticket on this room. I don't know why it's so cold this week. So hopefully they do something about that. I'm sure it's not just us who noticed. But I do, I think it's pretty well. So this E2 is going to have a little bit more calculus involved in it. So this is stuff that we're going to see on Tuesday, but you can kind of get a hint at what this is going to look like through some of today's lecture as well. If you've already started it, then this is sort of a key point, is that the integral from negative infinity to x is equal to the integral from negative infinity to something, let's say 0, plus 0 to x. And so when you get these piecewise PDFs that you have to integrate to get the CDFs, an important part is to break them up by their pieces. And a lot of times students will only end up integrating the one particular piece that they're sort of like, if it's got 4 pieces, they might only integrate piece 3 and they forget about the contribution from the pieces that come before it. So there's this constant offset, and if you don't do that, then your CDF won't be non-decreasing. It might actually it might look more like a PDF, the way it'll go up and then come back down. So that's kind of a tip here, but then there's a bunch of resources I put online about how to do this as well, and then we'll formally go over this in E2, and they also talk about it in the book. So there's a lot of resources there. The only other trick that I mentioned here is if y is equal to x squared and you're solving for x, remember that x can either be the positive or the negative root of y. And so this goes for all even powers of x. And so when you're solving for these inverse transform generators, you're going to want to choose the sign that ends up generating the appropriate range for that piece. And so if you're solving for a piece that represents, say, an outcome from -5 to 0, and you notice that after you go through the inverse transform calculation, you've got an option, either put a plus or a minus. Choose the one that ensures that your outcomes will go from -5 to 0. So that's kind of how that's done. And again, I've got examples of that online. Question? Well, so that's the kind of, so this will become more clear when you look at that. But so basically, if you've got a piecewise PDF, so this PDF has got 4 pieces. This piece goes from -infinity to 0. The next piece goes from 0 to 4. The next piece goes from 4 to infinity. Then, if you're integrating over that whole thing, then it's going to be difficult to integrate across the boundaries. So you have to integrate each piece separately. But when you integrate the middle piece, you have to remember to add in the contribution of the previous piece. And that's what I'm saying here, is that in order to integrate from -infinity to x, you can't just integrate. So if I've got a PDF that is specified like this, so it's got something up here, x plus 5, and then it might have 1/2 x, and then down here, x squared minus 2. So this isn't a PDF, but just imagine something that takes this form. And this is for some range, let's say from -infinity to 0, and this one is from 0 to 4, and this one is from 4 to infinity. Then if you're taking the integral of this thing, what people typically want to do is just to integrate this part separately and call that a CDF for that part, this part separately and call that a CDF, and this part separately and call that a CDF, and forget about all the rest. But what I'm saying is when you integrate this middle part, you have to not only take the antiderivative of this middle part and deal with the limits for this middle part, but you also have to add in the contribution of this part, basically the area underneath all of this part. And so the CDF of this middle, let's say I want to calculate f of x, where x is in this middle range from 0 to 4. The CDF of this is going to be the integral underneath this little part from 0 to x, plus the entire contribution of the area underneath this part from -infinity to 0. And it is that integral up here from -infinity to 0 that is often forgotten when people are doing these calculations. So that will become more clear on Tuesday. But for anybody who started to work on that, are there any other questions about that? We'll do several examples on Tuesday of that. Okay. So now I guess ICA-F, which is the midterm review, that's the one that's available. You can take that ICA as many times as you want. It randomly samples from questions from all of the ICAs before it. It's meant to be help reviewing for the midterm. So it is long, but you're not time limited on it. And again, you can take it over and over again, and it'll take your highest score. And again, because we have the drops as well, then you can also choose not to use it. What's going to happen is on the lecture day, lecture F, it will disappear, and so that's kind of going to be like the graded version will get saved to the grade book. But then a practice one will become available, which is identical to this one, but it just doesn't get scored in the grade book. So you've still got that practice exercise that you could use from the lecture until the midterm. So the lecture will be on a Thursday, the midterm will be on a Tuesday. So you'll have over the weekend to study that. By then, you'll have the solution sets for both of these homeworks, and I'll post a couple. I'm deciding on which midterms, which years to give you the same, but I'll give you at least 2 midterms, and we'll talk more about the midterm, during lecture F. But it'll likely be actually a scantron. But don't make it think it's. But the first time I did a scantron, I got the very lowest average I ever got in this class for a midterm. So my scantrons tend to be hard and very quantitative. So they can be. You just have to know how to do that. I'm not going to make it as hard as that first scantron, but I am thinking about posting that scantron as a sample midterm so you get an idea of what a scantron for this class might look like, as well as some of my older midterms, which took much longer for me to grade, but were all on paper. And so I'll at least post a sample of one of those, at least one scantron, at least one long form, to give you an idea of what I think about when I create midterms. So that'll be coming up by next week. Reminder, if hopefully you see this now, the labs are depending on the books. We usually start with a book exercise, so you've got the book as a reference, and then we build upon those. So make sure that if you're coming to the labs, then to bring your lab textbook, so you have that available. So any questions about admin or schedule? Okay. Good. All right. So so the motivation we've gotten so far, input modeling. There's input modeling in this Disney talk. We're selecting probabilistic models that make our modeling life simpler, rather than coming up with deterministic rules to capture all of the possible variation in real manufacturing systems. That's like trying to come up with rules to capture the variation in every molecule of air in this cold, cold room. So rather than doing that, physicists assume that those molecules move around randomly, and we assume that people show up to things like airports and such randomly, and we just have to pick the right randomness that is most representative of reality, and that is input modeling. So I went over last time several different common probabilistic models that we use for small components of the input models. As you start building your labs for lab 5, 6, and 7, which are all available online, then you'll see that for different parts of these, like manufacturing test systems, even though the whole system would be very difficult to model as a single probabilistic model, small subsets of a particular machine, a particular transfer time between machines, and so on, can be captured by relatively simplistic probabilistic models. So that's why I want you to get, at least for this class, these kind of bold models, uniform, triangular, normal, this kind of exponential family, exponential Erlang-Weibel, and the Poisson process, and then as well as on the discrete side, Poisson, Bernoulli, binomial, negative binomial, geometric. These are all useful to know, because when I describe a system to you, it might be described like, well, how many failures might we expect in this amount of time? And you might ask, well, what are some of the characteristics we know about the system? And that will end up honing in on, well, okay, so maybe I would expect to get something like an Erlang for this model, a Weibel for some other model, and so on. And so if you're doing that first lab 5, then most of those distributions for service time, I think they use a Weibel because it's very flexible, but they change the parameters for that Weibel. So certain parts take longer, but they're both distributed with sort of a Weibel distribution. We have to sort of know, well, why was a Weibel a good family to choose, and so on. So that's what we'll get to after the midterm, sort of why exactly you choose these. But for now, I want you to sort of start getting these into your vocabulary, and then we'll worry about the quantitative measures of evaluating which one's better for some data set versus another later after the midterm. But for now, at least try to understand the spirit of what's going on here. All of these probabilistic distributions are sort of the next kind of step up from random variables or random processes. And the big one I want you to know about is the Poisson process, which is one you probably talk a lot about in things like places like 470. And so the Poisson process, any random process, is just a collection of random variables indexed by something. It might be indexed by time, where it smoothly varies from 0 to pi to 5 to infinity, or it might be a discrete variable. It might be countable. It might be indexed by 0, 1, 2, 3. But the idea of a process is you collect all of those together for some reason, and then at each index, you've got a different random variable. So in a Poisson process, it's the count of events that occur up through time t. And we bundle all those together, and then we end up talking about relationships between those random variables. And so one thing we say is that in a Poisson process, what we're ensuring is that the time between events is exponentially distributed, and we usually give a rate parameter lambda. So that's this rate parameter associated with the Poisson process. It turns out it's identical to say, for any duration tau, then the count of events during that duration is going to be Poisson distributed with a parameter lambda times t. So if you look at the Poisson distribution, it's a discrete distribution. It has a parameter, sometimes called alpha. And if you replace that parameter with lambda times your interval tau, then you end up getting the count of events that occur in that interval. And those two things kind of go together. Now this is like the simplest thing. You usually sort of assume it as a basic thing that arrivals, let's say, to a bank or to a classroom or whatever, are described by a Poisson process, the number of students that arrive by a particular time, and so on. Now, it gets a little more complicated in reality. So this, what I've described here, is what we call a homogeneous Poisson process. That means that the rate doesn't change over time. But in real systems, we have what we're called non-homogeneous Poisson processes, where this rate varies over time. And we are going to simulate that in ARENA by allowing this rate to sit on a schedule. So when you, in lab 6, I think that's when we first introduced scheduling, and you can actually schedule capacities to vary over time. We also can schedule arrival rates to vary over time. And that's a simple way to sort of build a Poisson process on the input of your system, but then allow its arrival rates. So you have busy periods where you get a lot of arrivals per minute, and then the not so busy periods where they're not as much. And you just sort of are effectively scheduling different exponential rates for different periods per day. Question?
So you would say that a Poisson process is n Poisson distributions?
Yeah, you could. Well, it's a Poisson process is an uncountably infinite number of Poisson random variables. So any other questions about the distribution stuff going forward or just so far? Again, last time was mainly just an introduction to these, and so just gradually over the course, hopefully sort of start getting an intuition as to when to use an exponential and when to use a Weibull and so on. All right, so once we have a selected probability distribution, the problem is now, how do we implement that probability distribution? So it's great to sort of say, like, okay, I'd like to have exponentially distributed interarrivals, but how do I actually build a computer simulation that generates exponentially distributed interarrivals? And the other question that we use, kind of a little more jargon-filled question here, is how do we sample from a desired distribution? So how do we generate on a computer samples that are that come out with a distribution that is consistent with the one that we want? And so this is kind of the question here. So let's say I have X is a lifetime of a device that inspects cracks on an aircraft wing. I know that the failure times appear to be exponentially distributed. So how do I generate a simulation of failure times that has the appropriate timing? They show up at the right times. How do we make that work? And so what will be the major subject of the next lecture, E2, is this so-called inverse transform method, where if I have my desired PDF right here, I know the integral underneath that is the CDF. And so if then I take that CDF, I end up getting so this is just if I watch the accumulation of this purple area, it will, build up here. So this is the CDF for an exponential. And the trick is that once you have a CDF for any distribution, then if you generate a random number between 0 and 1 that's uniformly distributed, you can then sort of run it in the wrong side of the graph. So you can take it in this side here and map it to outcomes here. And those outcomes will have the desired distribution. And this is the inverse transform technique right here. And so that's what I'm saying we'll learn more about on E2. But before we get there, the real question is, how do we generate this to begin with? Certainly, Excel, MATLAB, R already do this for us. But the question is, what are they doing behind the scenes, and can we trust them? And if we needed to, to choose a different random number generator, how would we go about choosing that? How do we even judge one random number generator versus another? And so this question actually first came up, again, around the time of developing nuclear weapons, and when they were developing these Monte Carlo methods that we've seen before. And von Neumann, who was involved in some of these projects, actually had this nice quote where basically what they're looking for is how to generate deterministic, executable mathematical statements that could generate things that appear to be random. And so his claim was, you know what, I know we have to do this, but I'm a little worried about it because anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. And the reason I like this quote is that actually the first random number generators, when they actually look back in the literature, were investigated by Franciscan friars about 100 years before that. So it's kind of interesting to me that this weird connection here over time. But so where do we find them now? Well, actually, if you go to Amazon, you can search for random numbers, and you can buy a small book of random numbers. It's I forget how many pages this one is, but if you zoom in here, creative people who like to make use of chance in their work will find this a convenient source of random numbers. So there it is, right in the book. So there's a page of this book. And it seems funny, in good reviews, it seems a little funny, but actually once upon a time you could go to the library, a library like ASU's library, and there were these CRC texts that were filled with exactly pages like these. So, and they weren't, things that were meant as a joke on Amazon or anything like that. I mean, there was just pages and pages and pages. And that was when people needed to design an experiment or when people needed to test a new numerical method, then that's where they would get their randomness, is that this was sort of a trusted source of randomness. Now this isn't really practical for a lot of, for like Excel and MATLAB. They're not going to just call out to these books or even store all of these books. So then we sort of wonder, well, then how do they do it? Where do they get their numbers? And is it a reliable source? So I guess I'll pitch that out to you guys and say, well, let's say I had a 20-sided die like this one, and I wanted to judge whether a 20-sided die was fair. What are some of the properties that you think I would want of this 20-sided die? So take 30 seconds and talk to your neighbor and tell me what are good things about 20-sided die. How do I tell a good 20-sided die from a bad 20-sided All right, let's bring it back in. So when an operation researcher looks at a die, what are they looking for? So what is one good aspect? What is one thing that you want out of a 20-sided die? Anybody? There's multiple. How do I know that I got a bad die? So I roll a die maybe once, maybe several times, and how do I know that I got a bad one?
Giving you the same one?
Same number over and over again. That's one. How many people got that? How many people came up with that answer? It gives you the same number over and over again. All right, I'm sure more people than that, right? Okay, so same number over and over again. That's kind of, so that could be, what could be generating that? So that's like we'll kind of get into this. So let's say that, let's say it gives us the same couple of numbers over and over again. Let's make it a little easier to separate out these properties. So let's say I roll this 20-sided die, and it gives me a 1, a 4, and a 6. And every time I roll it, it only gives me a 1, a 4, and a 6. It doesn't ever give me anything else than that. So that is what I would say is a violation of uniformity. I am expecting to get every face 1/20th of the time, right? I mean, that's just kind of like, that's the whole point of this die, is that I roll it, you know, I'm playing whatever it is, Dungeons and Dragons, or whatever I need 20 sides for, and I am hoping that a face is going to only come up fairly 1 out of the 20 times. I have an equal chance of getting any one of them. So that's one thing that I'm saying. We want a die to have uniform outcomes, the same probability across all outcomes. But there is something else that's also captured, possibly in the outcome, that this idea that the same one came over and over and over again. What's another thing that I might want out of a 20-sided die, other than, even if I had uniformity? Let's say that I rolled it 100 times, and over those 100 times, I got roughly an equal fraction of maybe 200 times. I got a 10 of each of these sides, so I got uniformity. What's another thing that I want out of a 20-sided die, even if I already have uniformity, but it would still be broken if it didn't have this property? Yeah. Yeah, so I wanted to, that's a good point. Physically, I definitely wanted to show me one face. Is that what you're saying? I don't want to show that. Sure. So, and then let's think also sort of more, yeah. Well, so that we could test, I think that's going to get into some of the tests that we'll go into, the predictions coming out of this, but it isn't necessarily a property. It's something that you would notice maybe after a few rolls of the die. Yeah.
You're just going to put more numbers on it, so you're going to get a larger range of different values than
Well, let's say I'm okay with more than numbers. So let's say I like 20 sides. I like that each one of them shows up 1/20th of the time. But I'm looking for, if I wanted the 20-sided die, and I wanted it to be a fair 20-sided die, if I already know it's uniform, I get the sides 1/20th of the time, what's another way that it could be broken? No, that's scary. The same order, I like that, right? So what's the downside of the numbers coming up in the same order? Well, I guess I'm saying that, why is that bad? So if a die comes up at the same time every time, if it comes up in the same order every time, it's predictable. Exactly, I like that word, predictable. The probability of getting one face is, before you roll it, it's anything. It's uniform. It's across all those 1 to 20. But once I roll it and I see the outcome of the previous roll, then suddenly it's like it's like quantum mechanics. Like the wave function collapses. I suddenly know what the next roll is going to be. So even though over a long string, statistically, I might get every face 1/20th of the time, once I know one face, I know the next face. And that is what we call, it's a violation of independence. So if the probability of seeing one face does not depend upon the outcome of the previous face, then we say that those two rolls are independent. So those are the two things that we want out of a fair die. Uniformity, every face comes up the same fraction of time. And independence, one roll does not give us any information about the next roll. And those are exactly the two things that we need in a random number generator. We need uniformity to give us numbers approximately uniform across 0 to 1. And we need every number that's drawn not to give us any information about the next number that's drawn, and that's independence. So those are the two things we're sort of focusing on here, and this is them said a little more formally. So for each random number that's drawn, then this uniformity says that the probability density function is 1 across the whole interval. It has same density across the whole interval. It's a boxcar that comes up at 0, it goes over to 1, and it comes down. And so there's any interval shows up with the same probability. And so the expected value, you can think of it as sort of halfway in between there. But this captures that there. So one of the predictions here is if I divided that up into little n intervals. So let's add little n here, subintervals of 0 to 1. And I then have big N rolls of a die, or big N samples from this distribution. then I would expect roughly the same number of samples to land in each subinterval. So if I divide this up into 4 intervals, 0 to 0.25, 0.25 to 5, 0.5 to 0.75, 0.75 to 1, and I roll 10 times, then on average, 2 to 3 of them show up in each subinterval. And so that is an important prediction that we'll look for, we'll be testing. So if I was to look at a 20-sided die, a good outcome might be this one here, which is got a uniform distribution of outcomes, say from 0 to 20, but a bad outcome, which is kind of down here. If I look kind of closely at that, I see a lot of 7s. So I see like a 7, a 7, a 7, a 7, a 7, a 7, a lot of 2s, a couple of 1s, maybe a couple of 3s, 1, 4. So it really looks like certain outcomes are coming up more often than others. And so that is why this would be a bad die, because it's biased, and this would be a good die. Likewise, if we draw a bunch of these random numbers and we take a histogram, it better be flat across the whole interval. If it's kind of shaped a certain way, then it's a violation of uniformity.
So a uniform number should not come next to the same number, right?
Well, that is the next property, and that's independence. So this here is this is a property of one roll. So if I was to look at like aggregate across rolls, and I don't care about how they're ordered, then what's the probability that one roll comes from any particular area of this interval? And that's what uniformity is. The next thing will be independence. And independence is that if I have 2 rolls, and they aren't necessarily next to each other, they could be separated. But I don't want any roll to affect the probability distribution of another roll. So that's what I'm trying to say here. The probability of any future draw from this distribution is independent of any previous values that are drawn. So if I look here, say the good here, here's the same kind of uniformly distributed outcomes from a die, and here's bad, and it just increments. It goes from 1 all the way up to 20 and then back down. So if I was to take a histogram of all these bad outcomes, it would still be uniform, because I'm still getting them 1 out of 20 times. But it's bad when I zoom out and look at their order, and I see that, it looks like once I get a 4, I know it's always going to be followed by a 5. Once I get a 5, it's always going to be followed by a 6, and so on. So this is a violation of independence. So I used to give, and I maybe still will, questions on the midterm. Well, I'll give people sample outcomes from a random number generator, and I'll ask them if these look like good outcomes or not, just based on looking at it. And things I'm hoping people will look for are values that cluster around particular areas. That's a violation of uniformity, or patterns. And predictable patterns is a violation of independence. Yeah.
Okay, but in the example, it looks like there's a 1 every third almost.
Well, it might be, because I think I actually just came up with this by myself. I probably should have gone into MATLAB or gone to random.org and had it draw it for me. So this was intended to be. Now, the thing is, that still can happen. You can still have a 1 roughly every third. And so if I were to give you such a question on an exam, I promise it would be egregious. It would be obvious if you were new to look for it. And I would generate random numbers the right way. This is why randomness is so hard. If you just try to, there's all this stuff about, you can actually do an information theoretic analysis of numbers people choose or arrows that they press on their computer. And it turns out you can predict their pattern only knowing like once you see the last 2, you can pretty much predict the third like 80% of the time. So people are really predictable when you ask them to generate things randomly. So there you go. Apparently I like 1. Those are our 2 things, and so we need to figure out how to test for uniformity and independence before we gain confidence that we have a good random number generator. And if we don't, I knew a guy that he used to use a discrete event simulation package, not Arena, but one that back, like there was a particular time in the early 90s that he knew, and I'll talk about streams here in a second, there was a particular random number stream that would always give him weird results, and he just learned not to use it. And so it was just poorly implemented, and in that version, they hadn't fixed it. And so he just had to learn that that was a bad source of randomness. And so this really does happen. I'll show you another example here in a second. But here, any questions about that? Uniformity and independence. You should know those two properties and you should know their difference. And if I ever ask you what are the two most important things about a random number generator, that's the answer. This is like the Bloom's taxonomy, low order thinking or whatever, like you're just reciting answers, that's what you recite, uniformity and independence. A little bit higher order thinking, you should know the difference between them. Okay. All right, so so how do we generate true random numbers? We could throw dice. That's not really convenient if you want to draw a million of these things and have a computer do it. We could draw from a shuffled deck of cards or draw a ball from a well-stirred urn. Again, those aren't really good for automated systems. There are some interesting things that people do online. So there are setups where people put a webcam on a lava lamp, and then they basically take all the pixels out of the image that they get here and add them all up together and basically run a little bit of arithmetic and get a number out. That's called hashing. So, hashing an image of a lava lamp. So they're using the movement of the lava lamp to generate these random numbers. That might actually do a good job at uniformity, but I can't imagine this lava lamp moves that fast, and so it might be that the hash at 1 second might be very similar to the hash, half a second later. So not necessarily a great, randomness source. Sampling from atmospheric noise. If you go to random.org, and that's a common place people go, like when those of us who do experiments in the lab, if we need to randomize the order of things or those sorts of stuff, we often just go to random.org. It samples from atmospheric noise. And if you get randomness, really good high-performance workstation computers actually have circuits inside them where they sample from the heat of the computer, and that's where they get their sort of source of entropy. Yeah, question?
Is there a way that you can ever modify either independence or uniformity?
I don't know what you mean by modify.
Just for example, you have a series of random numbers, like clearly violating one of those properties, and you want to you modify the series to fit one of those properties.
Yeah, well, so you'll kind of see that, but independence. It turns out that if you sort an independent string, then the sorting makes it dependent. Or if you take a dependent or a correlated string and you randomize the order, you can make it independent. So that's sort of an example of that. And then there are ways, of course, like the fact that we're doing the inverse transform method where we take uniformity and we turn it into other things. There are certainly ways of taking, if you know the right functions, taking, like if I take exponentially distributed random numbers, which are not uniformly distributed, run them through their CDF, the output will be uniformly distributed between 0 and 1. So there are definitely the operations you can do to restore these things, but you have to kind of know what the distributions they came from in the case of uniformity. All right, so this is practical for small numbers, but if we want to do simulations on these machines, we might need to generate millions of random numbers extremely quickly. And so additional properties, so we always want uniformity and independence, but additional properties is we want these methods to be super fast. That's why these really simple arithmetic methods, if we can get them to work, are attractive. We want them to only repeat after a very, very long cycle. The downside of using arithmetic ways of generating random numbers is you're guaranteed they will eventually repeat. There's actually a proof of that. And so the computer-generated sequences will always repeat if you keep drawing them over and over and over again. So the challenge will be generating a random number generator that won't repeat until well after your experiment is done, so that when it repeats, it's during another experiment, and it won't necessarily create any weird correlations between your experiments. And then the other weird thing that, it might seem weird, is that all of these random number generators are going to start with some seed, which you should be a little familiar with after doing homework C2. And we want these methods to generate the same sequence given the same seed, regardless of what computer we put them on. And so it's kind of like I want 5 20-sided die. And I want this 20-sided die always to give me one sequence, and this 20-sided die always to give me a different sequence. All of these sequences need to appear uniform and independent. But I need to be able to take this die and give it to Ali, for example, and he can run it to maybe another country, and then it'll still generate the same sequence. And so there's a benefit of actually making our randomness portable. Now, why would that be a good thing? Can anybody think of a reason why I might want my random number generators to generate the same string of numbers given the same seed across a bunch of computer platforms? Think about what, if you're sitting at your job, you're sitting at Disney or wherever, you're doing your simulation, and you discover something interesting in one of your simulation runs. Then how might this property help you in communicating that to other people? It can be consistent. Some of you have noticed that if you haven't noticed, eventually some of you will, because I always get this question, but that when you rerun the same arena model over and over again after you restart it and you go into that reports view when it's working properly, then it will often show you the exact same stats that you got the last time you ran it. And you say, well, that's weird. Why is that the case? Well, it turns out, and I'll get into this in a bit, but Arena starts every simulation with the same seed. It starts new replications with a different seed. But every time you start Arena, it starts with the same seed unless you force it to start with another seed. And the advantage of that is if you discover something interesting in one of your simulations, you can then further investigate what was going on only by knowing the seed that was used in that replication. So I don't need to know the entire history of arrivals. As long as I know what seed I started with, then I can rerun that universe. It'll run exactly the same over and over and over again. So these seeds really do. They capture an entire universe of possibilities collapsed into a single number. And so if you want to communicate to someone else, you say, yeah, just open up my DOE file and run it with this seed, and you'll see this effect that I found. And someone will be able to do that on their machine and investigate that. Then you won't have to say, like, oh, shoot, I ran it, and it was really interesting, but I have no idea what the arrival times were, and so I just have to hope we see it again. As long as you have a way to reconstruct that seed, you can reconstruct those outcomes. So that's why we want that. The other reason why we want that is you've already seen the muffin sim. Remember, we ran the same muffins into two different simulations. Well, that's like running a muffin simulator, two different muffin simulators with the same seed. And that allows us to better compare the two muffin oven configurations because I run the same numbers into it. So I can run the two muffin simulators with this seed, the two with this, the two with this, the two with this, and I get these paired replications. Yeah.
So basically, that even if you start with the same seed, despite that it would generate different random numbers, we get the same statistics.
I get not only the same statistics, I actually get from the same seed, I get the same numbers. So it'll always be from this seed, it'll always be 20, 4, 2, 5, 6. And within that, it'll be uniform and it'll appear independent. But it won't exactly be independent because eventually it'll restart. But then if I start with a different seed, like whereas this one always started with 20, this one might start with 2, and then it'll generate the same numbers over and over again. So I get the exact same outcome every time I run. And that happens to also give me the same statistics, but it's even deeper than that. So that's why in Excel, you don't have access to the seed. And this became frustrating, I think, in one of your labs, because every time you saved, you got new random numbers. What inside Excel, they basically take a hash of the time. They basically take the second since 1970, and that becomes their random number seed. So every time you save a spreadsheet or update it, it basically reseeds the random number generator. And that's why at one time you'll get a certain string of random numbers, and at a slightly different time, if you've updated it, and I have updated it, that's why this time updated, you get a different string of random numbers. Unless you go into VBA, you don't have access to the seed in Excel, and that is actually frustrating. It's like, gee, wouldn't it be nice if I could control this seed? In Arena, you do. And so we'll see this more and more. This will become important in the back half of the class as well, but you should know it's there, is that there is a seeds element. It's in the elements panel. And if you drag that on, you can actually edit Arena's seed. By default, it always starts with the same seed. That's why when you run Arena over and over again, if you open Arena and run it, and then close Arena, and then open Arena and run it, you'll get the exact same results for the same model because it starts with the same seed. But if you go into this seeds element and you edit and this is hard to read here on this screen, but if you edit or add a stream 10, and you then put in a 5-digit number for the seed for stream 10, then Arena will use that number instead of its default seed. And so you have the ability to change the seeds in Arena. Turns out there's a lot of other cool things you can do with the seeds in Arena. So a real, any good simulation package will give you access to the seeds and will record the seeds in some way with your results so you can reconstruct those results. So any questions of that before we go into the types of, yeah? Why is it a good thing? So it's good. And so it's I say it's repeated, but what I mean is like it's not going to be repeated within this seed, but it'll just be repeated if I ever start with this seed again. And it's good because if I want independent replications, like if you say like I really want to simulate, I want to simulate the structure of this classroom, but for 5 independent days. Well, then I use 5 independent seeds, Monday through Friday. But if I say, I saw something interesting that happened on Monday, I just have to look up what seed that I used for Monday. And then I can rerun the Monday sim and then dive down deeper and see what was going on. So it allows me to rewind the universe by having control over the seeds. All right, any questions about that? All right, so now how do we build these arithmetic expressions that have all these properties? Well, again, in the nuclear, when they're first coming up with nuclear weapons, these are some of the first ideas that they came up with. And so this middle square method was sort of an early attempt. And it was like, say, well, what if we start with a 4-digit seed, and we're just going to square it to make it into an 8-digit number. And then we'll take the middle 4 digits of that 8-digit number. And that will, if we divide that by 10,000, that will be our random number between 0 and 1. And then we'll then use that in an iterative process as the seed for the next iteration. And so the idea is, here's an example up here. You start with 5197. Here's what it is squared. You grab these 4 numbers. That then is going to become the seed for the next iteration, and you divide by 10,000, and that's your output. And so the method, it appears to be simple to implement. But the downside is, if for many seeds, it'll degenerate to 0. So you can see down here that like these numbers get smaller and smaller, the squares get smaller and smaller, and eventually the middle digits just go all 0. So that's not good. And down here, if you start with a different seed, it might not degenerate to 0, but you very easily can get into these the same number over and over and over again. And so in this case, we started with 6,500, squared it, it gave us 2,500. Now when you take that and square it in the next iteration, you get 2,500 again, and then you're stuck. So this method tended to be not very good. It couldn't produce long cycles that were uniform and had independence. Here, you have sort of a violation of independence and uniformity because you end up getting a clustering around 0, and you pretty much can guarantee that it's always going to be decreasing. And then here, you always can predict the next number. And it's all sorts of reasons why this ends up being a bad approximation. So, there's other examples here where it appears to have promise, but so like in here, you might have a short transient period, and then you get into a little cycle. And so they say, well, what if I choose a better seed? Well, this seed appears to be good. It runs for 83, it has 83 numbers. Like this pattern here, there's no repeats or anything like that. And then at 84, it then gets stuck in another period 4 cycle. So you can have extremely long transients that end in these tiny cycles. So it might even be hard to detect, but eventually you're going to get into a point where if you run your simulation long enough, eventually you get the same interarrivals over and over and over again, even though early you had a good outcome. So that was no good. So it's simple to implement, and you only have to store these 4 digits, but it's difficult to choose a seed. It tends to degenerate to 0 or produce short cycles. So that ended up being a bad method. So they created other sort of things that were inspired by this. What if we took 2 numbers and we multiplied them together, and so on and so forth. And so I won't go into too many details here, but with these, you can kind of imagine all different ways that these things could go. They're all kind of similar, but we're just adding in, like here, they're multiplying 2 numbers, they're choosing the middle 4 of those 2 numbers. This is like the middle square, but instead of squaring, you're just choosing a separate number. And they were hoping that having two numbers would prevent these, but turns out it had pretty much all the same problems as the middle square method. So, the ultimate solution that we see in a wide variety of random number generators implemented in software now is this linear congruential generator, which is what you worked with in homework C2. And it has a relatively simple iteration. You define a seed, as we always do, a multiplier, an increment, and a modulus. And you implement this little formula where you multiply the seed, you add the increment, and then you take the modulus, which just basically takes the remainder. It sort of splits out anything above a particular, so like if it's 10,000 and it's 10,045 comes out of here, it just splits out the 45. And then you divide that by the modulus, and that gives you a number between 0 and 1. And there's a couple of different names the book goes over, depending on whether the increment is non-zero or 0. So if it's called multiplicative, that just means c is equal to 0. If it's called mixed, that means c is not equal to 0. And there's a bunch of other names you find in the literature. There's even other slight forms where they take the inverse. But the basic, if we look at how this is sort of implemented, and one of the nice things about it is you can actually do mathematics proving when you have situations where you have sort of as a maximal period. So, for example, this Hull-Dobble theorem states that you can have a full period so long as you set these three numbers, a, c, and m, up in this particular way. So there are numerical conditions, and I'm not going to test you on these conditions, but I just want you to see that there are numerical conditions that do not depend on the seed that guarantee that this thing has a full period. And that's really nice, because in the previous ones, some seeds had long periods and other seeds had not so long periods. In this one, every seed I put in will have a full period. But it's determined by this A, C, and M. So it's still sensitive to these, but if I choose them well, I get some good properties. And so the example, similar to what you did on the homework, we start with some seed. We've got a multiplier that goes in here. We add the increment here, and then that number there will end up. So this number here is 502 mod 100. Well, just 2 is the remainder when you divide 502 by 100. And then I take 2 divided by 100, and that's 0.02 is the number. And so if you iterate that over and over again, I take that 2 and I plug it in where the 27 was, and I end up getting 77, which gives me my 0.77, and I can then do that over and over again. So this gave me 52, which gave me my 0.52. And it turns out if I do this, if I choose these correctly, then I can get extremely long cycles here. So these numbers, I got 2,000 numbers from this choice of parameters here. And these 2,000 numbers, if I take their histogram, and so on 2001 it cycles, but these 2,000 numbers look pretty darn uniform. So this apparently has the properties that we want. The downside, though, is that it is very sensitive on its seeds. So if I go into R and I do that, bring up the help for rand u, which is one of the functions that can generate uniformly distributed random numbers, then it actually, at the bottom here, it has this note, and it mentions that this algorithm in rand u, it's sort of there for historical purposes. This is the algorithm that was implemented under these VMS systems. So that's kind of like an old kind of Unix-like system that was sort of popular in the 70s. And in these systems, even though they appeared random, when you actually plotted them in 3-space, and you saw that all the numbers landed on like one of 3 different planes in the space. So it wasn't uniformly distributed at all. You could sort of guarantee that the outcomes would always land on these planes. And so in future versions of VMS, they changed the parameters to prevent that from happening. So it's still not always perfect, and that's why we need these tests. The other downside of the big downside of linear congruential generator is by itself, it doesn't generate very long cycles. It only can generate cycles up to the modulus length. And so if the modulus length, you might think a million is a lot, but when you start running these simulations, your simulations might have 4 arrival processes, might have 7 service time distributions, might have a bunch of transfer times. Each one of those is going to require at least 1 draw from a random number generator. So you can easily accumulate millions of draws in one simulation. So you need extremely long periods. And so the simple solution to that is this so-called combined linear congruential generator, where all they basically do is take two linear congruential generators, and then they add them together. And by doing that, then even though each one of them has a small period, if they're generating numbers independent from each other, then the sum of them ends up having a much, much longer period. So here's a little numerical example here where it's kind of trivial, but I generated a linear congruential generator with a period of 4, a linear congruential generator with a period of 3. I took the subtraction of the two of them together, and the result here actually ends up having a period of 12. And that's even though the modulus of the congruential generator is 3. So even though the numbers here are only 0, 1, or 2, it actually ends up not generating a cycle until after 12 draws. So I can get extremely long cycles just from this simple method of adding these linear congruential generators together. So the takeaway I want you to get from that is that linear congruential generators have the promise of uniformity and independence, but they can have very short cycles. But we can correct that by combining multiple ones of them together, and that will end up generating much longer cycles by looking at their sums. Yeah. 3 times 4. Yeah, so that would take a little bit more mathematics to say for sure if it's always going to be these, but in this particular case, then yeah, it's kind of the beat between these two things that gives it the 3 and the 4. It's kind of like you played two harmonics on top of each other, and occasionally they would coincide, and then that would generate kind of a sub-harmonic, and that's what you're sort of seeing here, which it is happens to be 4 times 3. Yeah. Oh, this is one that I just chose for this example. In general, there are some guidelines for how to choose these things. I'm just not going over that, but yeah, I mean, this is just another parameter. Is that you choose the LCG parameters for these constituent LCGs, and then you have to also choose, whether you want to add or subtract them. You choose this modulus, and there are guidelines for how to do that. But just like there are guidelines to ensure uniformity and independence of the small ones, there are also guidelines to make this work as well. And just an example of that, there are combined generators now that you can find on computer systems like these that have periods that are like 3 times 10 to the 57. And so they're finally at the point where you can be pretty confident you run your simulation for a week. And you're not, imagine that the horror of that. If you run a week-long simulation, you find out that the last 3 days are just a copy of the first 2 days or something like that. Like that is the potential problem with this periodicity, is that you think you've run your simulation for and had a huge number of independent replications, but in the end, the back half of your replications end up being identical to the front half of your replication. So having these long periods helps ensure that that won't happen. Yeah. Sure, I think this is sort of the simplest implementation, but yeah, absolutely. For the kind of this harmonic thing, it's kind of like you get lower and lower subharmonics when you add all these other harmonics together. Then you can do kind of a similar thing there too. So I think traditionally these simple generators do the trick. But yeah, absolutely. I mean, the basic essence here is you've got one periodicity that doesn't agree with another. So if you add another, and then they all kind of don't ever line up at the right time until, it's very rare, and that's what ends up allowing us to do very well. So any other questions about generating these numbers before we get into the tests and some of these tests that you'll almost surely have to do on the midterm? Okay. All right, so we want to know how to test for these things, uniformity and independence. So, how do we do that? So, uniformity, we say that the output of the random number generator should be indistinguishable statistically from a uniform distribution from 0 to 1. So, if we were to formalize that, we want to do a statistical test where the null hypothesis is that each random number comes from U01. That's kind of we sort of don't want to reject the null. Now, we can never accept the null, but if we've rejected the null, if we've rejected uniformity, we know it's a bad number generator. And so we are going to sort of look at tests that have the potential to reject the null, even with very little evidence. So that's kind of what we're getting here. And, level of significance stuff here. So when I refer to level of significance, this is the probability that we will falsely reject uniformity even when we actually have uniformity. So we'll just set that in this class, usually to 0.05. And we'll get more into the sort of stat stuff after the midterm. So what test are we going to use? So if we drill back into your mind at 380, or farther back to Sesame Street, I suppose, if we divide, I mentioned earlier that if you divide this interval into subintervals, and then count how many outcomes land in each subinterval, then we would expect to get the number of samples divided by the number of subintervals within each subinterval. So I would like a statistical test to compare an expected count to an actual observed count. Now, do you remember in 380, what test do you use when you've got count data? I've got these number of observed counts and these number of expected counts, and I want to compare the two to see if they agree or not. Talk to your neighbor, take 30 seconds and think about what test you use. It's not a t-test. All right, let's bring it back in. So by the end of this semester, I'm hoping you'll all build up or start to build up these decision trees in your head as statistical tests, where under this case, use this test, under this case, use this test, and so on and so forth. And so here, the cue is counts. And so when I see counts, your mind should immediately go to certain types of tests. And so does anybody have an idea? And it's fine if it's not quite as immediate so far, that's what we're building up. But does anybody, after talking about it, thought about what test or compares counts? Chi-Squared, can you explain? You think 380, there's probably, the downside of 380 is you're probably like, you remember the t-test, you remember the Chi-Squared, and so if it's not the t-test, But, so the Chi-Squared is what I'm looking for here. So a Chi-Squared is a test you use on count data. So a Chi-Squared test is when you have an expected distribution of counts. And in this case, it's simple. Every bin is going to have the number of samples divided by the number of subintervals in it. And then you're going to then actually have an observed number. And for each bin, it'll be above or below that expectation. And then you look at those errors. And the Chi-Squared quantifies whether the error you see could be explained just by random chance under the null hypothesis of them being equal, or if it's a significant variation. So we're comparing expected frequencies and observed frequencies. So remember that Chi-Squared, if I ask you to compare frequencies or counts, the first thing you can think of is Chi-Squared. You might think of the Fisher's exact test too, if you've heard that one. And there are reasons why we use that. For today, we're focusing on Chi-Squared. Now, Chi-Squared can really only be used when you have a lot of data. You cannot use a Chi-Squared when one of the expected numbers is less than 5. When it is less than 5, you either have to modify how you're using the Chi-Squared or use a totally different test. And we'll get into that in a second. So let's see what I mean here. So the basic process, we take our capital N observations. I might, on a midterm, I'll just give you, I'll say, we'll divide the interval up into 4. You divide the hypothetical interval. I get this problem in midterms a lot. If I give people data, they'll look for the minimum value in the data and the maximum value in the data, and they'll call that their interval. But we're testing the hypothesis of uniformity across all of 0 and 1. So we divide the hypothetical interval up into those subintervals. So if I say 4 subintervals, just divide 0 to 1 into 4 subintervals. And then you should be able to then take however many observations were there, let's say there are 100 observations, divide them by the number of subintervals, and that tells you how many we expect in each subinterval. If that expectation is less than 5, then you cannot use a chi-squared test, again, without modification to the test, or just you have to find a different test. And then we can count the number of observations landing in each one of these subintervals, and then we compute this statistic, which hopefully looks familiar. After the midterm, we'll talk about this statistic in more detail, like why the heck is it squared in the numerator but not in the denominator? Like, I always had a problem with that when I was at your stage. I looked at this thing and I said, units don't work. You know, I get squared units in the numerator and not squared in the denominator. So what's up with that? So we'll talk about where this comes from and why it actually makes sense later. But for now, I just want you to see that it basically is calculating a deviation from expectation. And it is normalizing it by that expectation, and then summing it over all of those subintervals. So that's what the chi-squared statistic is. It is a measure of deviation from expectation. A large chi-squared value is bad. A small chi-squared value is good. So your threshold that you look up in the back of the book is going to be how big can it be for us to accept it as being possible just by chance. So if I think I've got an example here. Let's say I give you these data points. There's 30 of them here. And I say, let's do 4 intervals, 4 subintervals. So I create these 4 subintervals, 0 to 2.5. So 2.5 with subintervals from 0 to 1. And then, so the next step here is I can count the number, it's slightly out of order from the previous slide, but I'm going to count how many of these 30 land in each interval. And if you were to go through each one of these, you see there's 3 that are in this interval, 4 in this one, 8 in this one, and 15 that are in this one. And then I figure out how many would I expect. Well, if I've got 30 observations, if they were uniformly distributed, I'd roughly get 7.5, so 7 or 8, in each subinterval. So that allows me to calculate the chi-squared statistic, which is just a sum of 4 numbers. So this is kind of the deviation for the low subinterval, the deviation for the 2 middle ones, and the deviation for the outer ones. So I see the observation number, 3, 4, 8, 15, and the expected number, 7.5, 7.5, 7.5, 7.5, all divided by 7.5. And that gives me this number out here, 11.8667. That's my chi-squared statistic for this. So then I have to go back into a table, and I will give you these tables on a midterm. But in the back of your book, your lecture book, it's in table A6. And I now need to be careful about choosing. So I won't tell you where to look, so you'll have to know this. For the chi-squared, the degrees of freedom, and again, we'll talk about what that means after the midterm, but for now, just remember that it is 1 less than the number of subintervals. So there are 3 degrees of freedom with a chi-squared, using 4 subintervals. If I used 8 subintervals, it'd be 7. So I look in row 3, and then the columns here are organized by that alpha value. So that type 1 error, acceptable type 1 error. And that's 0.05. And so I find that my critical chi-squared value is 7.81. Now down here I see that 11.866 is way bigger than 7.81. So this deviates far more than my expected frequency. Far more than our expected counts, so we reject uniformity. And that, I think should make sense if we kind of look at it. 15 of these fell in this interval from 0.75 to 1, and 8 from 0.5 to 7.5, and hardly any in these. So it really doesn't look very uniform, and that's exactly what the test is. Questions about the chi-squared? Hopefully review. Okay. So the chi-squared test, if you have too few samples, you have to use the Kolmogorov-Smirnov test, which the sorting hat, which involves sorting the numbers. And so you guys have been introduced to this already. And I might end up going into more detail about this. Actually, we'll finish this one, and I'll stop a little early before this independence here. And we'll cover that the next time. So with this one here, this is the table that you set up in your homework, but a different set of numbers. And the idea here is you sort the numbers. And the basic, if I look up here, if I'm in the samples from a uniform distribution, then basically I would expect, if I just sort the numbers, the number that is in the lowest in the order should sort of show up between I minus 1 over n and I over n. And the one next in the order should be in I over n and 2 over n, or 1 over n and 2 over n. So basically the numbers, if I were to look at these numbers when they're sorted, I would expect this first number to show up between these two numbers. This second number should show up between these two numbers, and so on. Because if they're uniformly distributed, they should be peppered kind of equally across everywhere. So if I cut the thing up, that's where I'd expect it to be. So what you're doing in every column is calculating the difference from the actual data point in blue with the two boundaries and taking the largest difference. And that you then bring together the largest of the largest differences, and that becomes your D statistic, which you compare to go to table 8.5, and you look up, and in this case, the degrees of freedom are the actual number of data. And then the alpha is the alpha that I give you, so at 0.05. And so for this, the critical value is 0.65, the D value is 0.26, and again, D you can think of as a difference, and this is not big enough, and so we do not reject uniformity, but that might still mean that we could detect deviations in other tests. Sort of just, I'll cut ahead here, and then I'll take that last question. But what's happening more generally is what you're doing is you're plotting effectively the sample CDF. If you sort all of your sample data and then plot them against I over n, you end up getting this, which is an approximation of the CDF. Here are all my data points. This is the first data point. This is the second, the third, the fourth, and the fifth. And that's what caused them to go on these stair steps. And I can then plot a hypothetical CDF against it and measure the difference. And that's all the chi-squared test is doing. So here's an example with, and this is a normal distribution, normally distributed data against a uniform, a huge difference. And, this is exponential data with a uniform, huge difference. Weibull data, huge difference. And then finally, uniformly distributed data, and it's right along that line. And so there's very little difference. There's a question there?
Yeah, so that's it's not uniformly distributed because 0.81 exceeds the upper.
Well, it's okay then to be exceeded. Like that just can happen by chance. But this D alpha that you look at in the back of the book, that sets the critical value and what's the worst it could do.
Fast forward to the graph, the x-axis, what are you plotting it on the x-axis?
The x-axis are the actual data points. Okay. So 0.25 was the earliest in the order, so then it gets plotted against 1 over 5. And then 0.35 is the next one, so it gets plotted against 2 over 5, and so on. All right, so let's do an attendance. Don't forget about the 6 p.m. thing. And the question I'll have then for today is, what is, if I want to, so that's good. If I want to compare counts, and I have a lot of data, so I have a lot of data, and I have expected counts versus observed counts, what's the test I should use? So if I have observed frequency data, observed counts of data, and expected counts, and I have a lot of data, then what test should I use?